Hello everybody. Well, if you missed the last lecture on oxidation reduction, particularly the one on calculating oxidation numbers, then please use this one, which will give you a rundown of how it works again. Now, just to reiterate from the previous lecture on oxidation reduction, the reason that we need to know what the oxidation numbers are of particular elements in given situations, for instance, as a product or as a reagent. The reason we need to know that is so that we can predict where things are going to be in any given chemical reaction. Okay, so for instance, if copper sulfate reacts with zinc, then we'll end up getting an oxidation reaction that will reduce the copper to copper metal, and the zinc will be oxidized to form zinc sulfate. Okay, so let's have a look at this. First of all, we have the rules. So these are rules developed over a long time with a lot of experimentation, and of course building up a model that works, in other words, that we can make predictions from. So hence this oxidation number model. Alright, so let's have a look at rule number one. Okay, so rule number one: oxidation number of an element is equal to 0. The example that I've given you there is copper is equal to 0, aluminium is equal to 0, sulfur is equal to 0, and nitrogen gas is equal to 0. So the N in nitrogen gas would be 0. Okay, so that's the first rule. First rule is if you have an element, just a pure element, then the oxidation number of that element will be 0. Okay, let's move on. Okay, so rule number two: the oxidation number of a simple ion is the charge of that ion. Okay, that's pretty straightforward. Oxidation number of a simple ion is the charge of that ion. So I haven't got an example up there, so I'll do that now. Let's say, for instance, silver, so Ag, the charge is normally +1, so the oxidation number in this case will be +1. Oxidation number of let's say sulfur just by itself, that's sulfur is normally -2, so the oxidation number is -2. Okay, so we've got silver as +1 and sulfur as -2. Okay, so that's pretty straightforward. That explains that particular rule. Okay, next one. The oxidation number of hydrogen in non-metallic compounds, okay, is +1. So normally the oxidation, the valency of hydrogen is +1. So generally the oxidation number of hydrogen will remain as +1. For instance, in the product like this, like HCl, the oxidation number of hydrogen in hydrochloric acid is +1. It's an example. However, there is an exception to this, and that is in a metal hydride. So metal hydride is really a metal that also contains hydrogen. So in other words, hydrogen bonding with a metal, sodium hydride, potassium hydride, calcium hydride. These metals only contain the metal, whatever they are, and hydrogen. So Let's have a look at this particular example. So oxidation of hydrogen in the metal hydride is -1. Okay, let's have a look at an example of that. All right, so here we have sodium hydride, as you can see there, sodium hydride, and sodium would normally be +1, and the hydrogen as a result of that would end up being -1. So you can see here why under this occasion H becomes a -1. Okay. All right, so that's rule number 3. So I'll need you to watch out for this in subsequent examples. Okay, number 4. Okay, the oxidation number of oxygen in a compound is usually -2. All right, so that's 99% of the cases where you've got that oxygen in a compound like that, then the oxidation number is going to be -2. All right. So, however, again we have exceptions, and the one exception is where the oxygen forms a peroxide. So, what's the difference between a normal oxygen ion and a peroxide? Or normal oxygen ion is just O2 minus, so in other words, one single atom of oxygen with a valency of 2 minus, whereas a peroxide is 2 atoms of oxygen with a valency of -1. Okay, so let's have a look at an example. Say hydrogen peroxide, sodium peroxide, and so on. Let's have a look at that. Okay. As I said there before, O2 negative, so that means that this is the ion, O2 negative, for instance in hydrogen peroxide over here, the H is 2 lots of H plus ions, and one O2 minus ion. Okay, therefore we've got H2O2. Okay. H2O2. All right. So again, sodium, 2 lots of sodium ions, 1 of the peroxide ion, which is negative. So the plus and the minus, they will equal to 0, which of course you know is going to be 0. Other examples, for instance, magnesium peroxide and calcium peroxide, for instance, will be other examples of this. Okay, alright, actually what I might do later on in the example there is put down an example of a peroxide. Might be more useful as an exercise. Okay, so let's have a look at the next one, which is number 5, and number 5 says the oxidation number for fluorine is always -1. Well, there's no exceptions in that. So whenever you see fluorine, first of all, deal with that oxidation number, because that's always going to be -1. Okay, everything else from that is calculated relative to that particular oxidation number. All right. Okay. All right. Question. Rule number 6: the sum of the oxidation numbers in a neutral compound is 0. So any neutral compound, carbon dioxide, water, you name it, it's a neutral compound. It will have an oxidation number of 0. In other words, the sum of all the oxidation numbers in that particular compound ends up being 0. Okay. All right. So here's some examples. What did I write down here? Calcium oxide, for instance, would be 0. The calcium is 2 plus. The oxygen is 2 minus. The two of them add up together. 2 plus 2 and plus 2 minuses make 0. And that will apply to any neutral compound. Okay. All right. Next one, the oxidation number of a polyatomic ion adds up to the charge that's on that ion. So first of all, if you're not familiar with the term, then a polyatomic ion means that it's an ion that's comprised of several well, more than two, if you like, two or more atoms that are bonded together, and although they're bonded together as a group, they still become an ion. For instance, in this example we have nitrate. So nitrate, nitrogen, 3 oxygens, in that combination has a charge, a leftover charge. The valency becomes -1, so it's polyatomic, more than one atom, and it has a residual charge. And the rule is saying that the oxidation number of that particular ion, that nitrate, is going to be the same as the charge. So the charge is -1, so therefore the oxidation number is -1. Let's have a look closely at it. So NO3 is -1. If you have a look at that, there's 3 oxygens. We've already established from a previous rule that oxygen is going to be mostly -2. So the 3 of those would end up being -6. Okay. Now follow this closely, please. If the oxygen is -6 and there is a residual of -1, it follows that the nitrogen must be +5. The oxidation number in this particular polyatomic ion must be +5. It's the +5 and the -6 that gives us the residual -1. Okay, so that's how that works. We'll look at some other examples later on, and well, when I give you your worksheet, you will see some other examples like this, which I want you to follow. Okay, let's carry on. Okay, number 8, in a covalent compound, so it's bonded in a covalent bond, carbon dioxide for instance. Okay, if the covalent bond that does not involve hydrogen nor oxygen, so carbon dioxide wouldn't fall into that group, into this rule. Okay, it wouldn't fall into this rule. Okay, it must not have oxygen or hydrogen for this rule. The more electronegative the number, the more electronegative element becomes the one that's assigned a negative oxidation number. Okay, so for instance, I've got an example here. We've got iodine and chlorine as a compound. Iodine and chlorine as a compound, so iodine trichloride here as a compound, ICl3. Now both of these are halogens combined together, and but however the difference is that chlorine has a higher electronegativity than iodine. Okay, so chlorine has a higher electronegativity than iodine. So therefore, according to this rule, chlorine will take the negative oxidation number. Although in normal circumstances, because iodine is a halogen, it would normally be -1. But in this case, where iodine becomes part of this particular compound, then iodine assumes a different oxidation number. Let's have a look. So here we have iodine. Cl is more electronegative, so the Cl will take the -1. So in other words, 3 of those, it will be 3 times -1. So the Cl will be -1 in this case. And of course, the iodine has to be +3. Okay, the iodine on its own has to be +3 to counter the 3 times -1 of the chlorine. And again, once more, the chlorine is the one that takes the negative because it is more electronegative than iodine is. Okay, so that makes the rules. Now let's have a look at an particular example, and I've got an example here of magnesium hydroxide. Let's have a look at magnesium hydroxide, NaMgOH2. Alright, so according to the rule, if we have a look at the rule, and we're going to say that, that a particular compound, so the sum of any neutral compound is 0, so rule number 6. Rule number 6, this satisfies rule number 6, so the whole lot is equal to 0, satisfying rule number 6. Okay. Then we have a look at its individual components. So here we have magnesium. Magnesium under rule number 2, of a simple ion is the charge on that ion. Have a look at there. Rule number 2 would make that magnesium the oxidation number for that magnesium +2. Okay, using rule number 2. Let's look across and see what will we do for oxygen. For oxygen, we again rule number 4. We're talking about oxygen in a compound generally being -2, and in this case we have actually this is meant to be, this should say -2, yeah, -2 plus -4. Okay, so here we have this satisfies rule number 4 for oxygen, and of course we have two of them in the hydroxide, so you can see the two of them in the hydroxide, so they will come to -4. Okay, so that'll be the 2 over here, the magnesium, the 4 over here. Now of course, let's have a look at the hydrogen. The hydrogen, which rule is that? Okay, so that's rule number 3. Rule number 3, we're saying that hydrogen will generally have with a non-metallic compound, would have, actually this should say with a, not non-metallic, with any compound. I should just say this, hydrogen in a compound is +1. Actually it's a this wouldn't shoot negative rule 3. This would actually satisfy this would satisfy rule 2. Okay, this would be rule 2. That would satisfy rule 2 being a simple ion. So that would be H plus. So that would satisfy that rule, not rule 3. Okay, rule 3 is quite specific about being a non-metallic compound, being +1. So it refers to a non-metallic compound, not a metallic compound of any description, and its exception over here in rule number 3 refers to a metal hydride. So this magnesium is not a metal hydride. It is not a non-metallic compound. It does not comport with rule number 3. So this actually belongs in rule number 2. So let's clear this up. So we've now had magnesium is +2. 2 of those. We've got 4 of these oxygens. We've got O2 and negative, and we've got a further 2 +2 of hydrogen. That gives us now an overall oxidation number of 0, which is the compound. Okay. Okay, so let's have a look at some specific examples down here of some oxidation numbers. Let's see if we can work them out. Well, here we have, we're starting off with sodium chloride, and sodium chloride has an oxidation number, it's a neutral compound, has an oxidation number of 0. Okay, so we can see that sodium obeying that rule number 2 has an oxidation number of +1, and chlorine has an oxidation number of -1, so also obeying that rule. So the sodium is +1, the oxidation number of chlorine is -1. Let's have a look at sulfuric acid. Over here we've got H2SO4. So again, the hydrogen is +2, 1 each. Okay, so it's +1, so it's 1 each, so it ends up being +2 as a combination. And then we've got oxygen. Let's look across here at the oxygen. The oxygen, we've got 4 of them, so therefore the oxygen will be -8. Okay, 2 each, -8. So they come up to 0, so it follows that the sulfur must be plus 6. So then that is indeed what it is. So the oxidation number for sulfur in sulfuric acid is plus 6. Okay. Let's have a look at this tricky one, calcium peroxide. So calcium peroxide, remember that's a special one over here, because oxygen, while oxygen generally has an oxidation number of -2, peroxide is a special case where oxygen is just -1. Okay, so let's have a look at that. We've got calcium peroxide. So calcium satisfying rule number 2. But not only that, rule number 2, but there are some other rules. If you might come across slightly different rules to this, and one of those rules will be that anything in group 1 will be +1, anything group 2 will be +2, and aluminium is +3. So there are some iterations of these rules that specifically name group 1 elements, group 2 elements, and aluminium. So being +1, +2, and +3 in that order. Okay. So again, here we have calcium being +2, oxygen, each of them, there's 2 of them, and both of them are -1 because they're acting like a peroxide. So therefore, that would make them -2. So therefore, that's why calcium peroxide is 0 as a combination, those 2 oxidation numbers. Let's have a look at the last one over here. What have we got here? We've got silver nitrate. Okay, again, it must add up to 0. Alright, so therefore let's have a look at the oxidation numbers. So silver acts like a group 1 element, so it's +1. Silver will be +1. And then let's have a look at the oxygen over here so we can determine the nitrogen. So it's not something that you would normally expect of nitrogen, so you'd be looking at normal simple ion for nitrogen, and you'd be expecting it to be -3. However, in this particular situation, that's not its oxidation number. Okay, so let's have a look at the oxygen. The oxygen which is conforming to the oxygen rule up here. Okay, rule number 4, and because it's conforming to that rule number 4, we have 3 lots of them that come up to -6, and because of that, the nitrogen must be 5, +5. So it's the +5, the +1 that makes the +6, and that opposes the -6 for the oxygen, and that makes silver nitrate have an overall oxidation number of 0. Alright, my advice is get lots of practice, okay, and make yourself very, very familiar with these rules. Certainly you'll need them to be able to do the oxidation reduction analysis of various chemical reactions. Okay. All right. So if you're interested in this type of thing, then please press the subscribe button, and if you did like it or didn't like it, press the like or the dislike. That's your choice. The next thing we're going to do is we're going to have a look at the galvanic cells. So we still have this problem going on, so I imagine that there'll be more online stuff, and I will post some of these lectures if not enough people are showing up online for the normal lecture. Okay, so far so good. You've shown up, and so I haven't had to do many of these, but I think I probably will in any case, because you might find it useful to go over it, and make better notes. Okay. Alright, so again, press the subscribe button, press the like button, whichever you choose. Thank you very much, and I'll see you next time.